In this work, we explore holographic beamforming using dynamic metasurface antennas for future 6G systems. This research is carried out at the University of Essex 6G Lab as part of a Horizon Europe Marie Skłodowska-Curie doctoral network. Focused on enabling secure and intelligent communication at massive scale, this work is supported by UK research and innovation. Let us begin with the motivation. Let us consider a smart factory environment. Autonomous robots are moving and communicating wirelessly, while intelligent surfaces dynamically shape electromagnetic waves to maintain reliable links. These architectures enable scalable and low-cost communication by directly controlling wave propagation through reconfigurable surfaces. Since the surfaces themselves are tunable, the need for expensive RF front-end components, such as RF chains and power amplifiers, is significantly reduced. This makes them a strong candidate for extending current MIMO systems toward extremely large-scale arrays with thousands of elements. Dense metasurface elements integrated on dielectric substrates allow more radiating elements within the same physical area, enabling higher communication capacity. However, physical constraints limit their performance, motivating the need for efficient optimization methods. Let us introduce the conventional fully digital multiple antenna architecture. In this model, multi-stream communication is achieved through digital pre-coding, with each antenna connected to a dedicated RF chain. This enables independent amplitude and phase control, allowing precise beamforming across the array. However, this flexibility comes at the cost of high hardware complexity and limited scalability for large antenna systems. Let us now move on to an experimental demonstration using a conventional setup. We consider a two-user scenario where one user is fixed and the second moves angularly away. The beam tracks the moving user, maintaining alignment throughout. With fully digital architectures, independent amplitude and phase control enables highly focused beams, resulting in low interference and reliable communication. As the users separate, interference decreases, but toward the array edge, reduced gain requires higher transmit power. While effective, this approach relies on dedicated RF hardware per antenna, making large-scale systems difficult to scale. This brings us to dynamic metasurface antennas. Here, multi-stream communication is enabled through a hybrid architecture where part of the pre-coding is realized via analog beamforming. This reduces the need for RF front-end hardware at each radiating element. The operation relies on the Lorentzian tunable response of the elements. However, this introduces physical constraints, limiting beamforming performance, often overlooked in conventional methods. Now, let us look at the same two-user setup using dynamic metasurface antennas. Beamforming is achieved through the metasurface, with the beam adapting to track user positions. A comparable transmit power is achieved relative to fully digital systems, while requiring far fewer RF front-end components, around 1/20th of the hardware. This is enabled by the Lorentzian response of the elements, which also couples amplitude and phase, limiting control. As a result, side lobes appear, increasing interference. This highlights the need to improve efficiency by better focusing the transmitted power. To address these limitations, we propose an adaptive beamforming approach for dynamic metasurface antennas. The method introduces an adaptive radius Lorentzian-Constrained holographic model, enabling a flexible search space for metasurface tuning. This bridges the gap toward ideal unit circle phase alignment. By shaping the response along a Lorentzian manifold, the approach improves amplitude and phase matching, resulting in enhanced beamforming. Now, let us see the impact on the same setup. Observe the side lobes in unintended directions, which are significantly reduced compared to the previous method. This is achieved through improved optimization of Lorentzian-constrained weights, enabling more consistent amplitudes. As a result, amplitude and phase matching improve, bringing the response closer to ideal alignment. This leads to better energy alignment toward users, reducing unwanted radiation. Consequently, interference is minimized, and the beam becomes more focused and efficient. Importantly, this gain is achieved without increasing hardware complexity, preserving scalability. In summary, dynamic metasurface antennas enable densely packed arrays, making them a strong candidate for future extremely large-scale systems. They offer low-cost, low-complexity architectures, and with our proposed approach, their performance is further improved. For more details, please refer to our papers listed here. You can also find our contact details for any questions and potential collaborations. Thank you for your attention.